guys, so welcome to our first AP Bio video. We're going to start by talking about metabolism. So metabolism is just an organism's, the totality of an organism's chemical reactions that power the energy of life. So cellular respiration, for example, extracts energy that's stored in sugars and other fuels that we put in our body in the form of food and apply this energy to perform work. So our cells do all kinds of work, of course, like growth, reproduction, maintaining homeostasis, and also all the mechanical work that happens within cells. Some organisms are even able to capture this energy from their environment in one way or another and convert that to light. So bioluminescence is a really cool adaptation that some animals have and other organisms have for a variety of reasons. I showed a firefly right here. So there's actually a lot of cool stuff about how fireflies of different geographic locations or of different species will blink at different durations to signal to mates or some other type of communication. So cool. So we are going to talk all about how organisms are able to capture this energy from fuels and turn it into work for a variety of reasons. So as I have said, metabolism is the totality of an organism's chemical reactions. And each of these chemical reactions are powered by their own specific enzyme. So here we see a metabolic pathway where we have one starting molecule in an enzyme that facilitates a certain reaction to get to the next molecule, which is B in this, just like general example of what a metabolic pathway looks like. And eventually, after a total of 3 enzymes and 3 reactions, we get one product. Now, what I do want to note here is that pathways can have multiple starting molecules, so this one is a little bit simplified. So there's 2 types of metabolic pathways. There's anabolic pathways and there's catabolic pathways. I know you guys have heard these words before, but let's just go ahead and go through them right now. So anabolic pathways, you might have heard of like anabolic steroids before. And while that's, again, a little like simplified and thinking how those are related, you can remember that anabolic steroids build up your muscles. And of course, I have the cat over here on this side that is destroying something. And it looks like that's like a candy aisle or toy aisle. I don't know. So catabolic pathways are whenever large molecules are broken down into smaller ones. So in catabolic pathways, we are going from a complex to a simple structure. So complex molecules to simple molecules. Energy is released, and the products are now in a lower energy form relative to the original starting molecules. An example of this is cellular respiration. We can also think about anabolic pathways when we're building molecules, building that muscle with our anabolic steroids. So we start from more simple molecules and assemble larger, more complex ones. Energy is required to do this. So our cells have to put in energy to perform anabolic reactions. And in anabolic reactions, our products are at a higher energy form relative to the starting molecules. An example of this is photosynthesis. So you'll hear lots of different definitions for what is energy. You'll hear that that energy is the capacity to cause change. You'll hear that the energy is the ability to rearrange a collection of matter, which I kind of like that definition. That one's cool. But what you'll probably hear most often is that energy is the ability to do work. In the quantitative study of the transformation of energy in organisms, it's called bioenergy. So what are the forms of energy? Well, there's kinetic energy, which is energy that's associated with motion. And a type of kinetic energy is thermal energy or heat. So we know that energy is the capacity to work, but how can heat really do work? Well, this guy over here is named James Watt. So James Watt was a physicist and a chemist, and he is, you might recognize his last name, Watt, as the SI unit of power. like a wattage of your light bulb, but he also invented the steam engine. So anyways, what this guy did is he showed that heat does have the capacity to do work, because if a pot is on the stove and it's boiling over, that heat can actually cause the pot lid to lift off, meaning it's doing work. So this type of energy is able to be harnessed to do work. Same thing with light. So in photosynthesis, plants are able to harness light energy to then perform work. Potential energy is energy that matter possesses just because of its location or structure. So like this water behind the dam, or the diver at the top of the diving board has potential energy. The potential energy that we're really going to focus on is chemical energy. So that's energy or potential energy that's available for release within a chemical reaction. Glucose, for example, has very high chemical energy, which is why we use it for so many of our processes. What we really have to remember here is that energy can be converted from one form to another. And thermodynamics is the study of those energy transformations. So let's get a little bit into thermodynamics. So you'll hear isolated systems and open systems. Isolated systems are unable to exchange energy or matter with their surroundings, kind of like a liquid inside of a thermos. And then an open system is whenever the energy and matter can be transferred between the system and its surroundings. So organisms are open systems. We are able to exchange matter and energy with our surroundings. So let's talk about the first law of thermodynamics. You'll also hear this called the principle of conservation of energy, because what it says is that energy can be transferred and transformed, but it cannot be created or destroyed. So the energy of the universe is constant. Plants are like energy transformers, not technically producers, which is kind of interesting. The electric company doesn't make energy, but they capture it and convert it to a more usable form. The second law of thermodynamics states that every energy transfer or transformation increases the entropy of the universe. What is entropy? What does that mean? Well, entropy is the measure of molecular disorder or randomness. So what this law really says is that our universe is moving from order to disorder. Sometimes some of this energy is usable, and we are able to capture that energy to do work, but most energy is unusable and lost as heat within organisms and systems. So let's look at this example of our two laws of thermodynamics. So the bear is taking in chemical energy and transforming that energy into a few different types. One, kinetic energy, energy that's available to do work for the bear. Lets him run around, lets him go get more fish and do all of his other bear things. But a lot of this energy is transformed, a lot of this chemical energy from the fish is transformed into thermal energy and is lost as heat to the surroundings. Now, the consequence of this is that the surroundings become more chaotic. This bear is actually creating disorder in the universe. What does that mean, biological order and disorder? So, animals are consuming complex molecules in their food, and they're releasing smaller, lower energy molecules, like that carbon dioxide in the water, and also heat into the surroundings. So living systems, organisms, are increasing entropy of their surroundings. But we also know that organisms create ordered structures from less organized forms of energy and matter within their bodies, within the system. How can both of these be true? To think about that, we have to go back like 4 billion years ago. So let's kind of look at this tweet to see what we're talking about. So this person said, I was born in the wrong generation. I wish I could have been created as a chain of amino acids floating aimlessly in water during the biochemical creation of living organisms. What are they talking about? They're talking about this thing called primordial soup. So primordial soup is just this hypothetical set of conditions that existed, like I said, 3.7 to 4 billion years ago. So there was really simple molecules floating around in this soup, in this water, and eventually these molecules were able to find each other and create more complex molecules, and eventually arising to an organism. But how can this be true? Because we know that the universe is moving from order to disorder? Well, the evolution of more complex organisms from simple organisms does not actually violate the second law of thermodynamics. And that's because while the order inside a particular system or organism may increase, there's more order inside the organism. That organism is increasing the disorder of the universe, of its surroundings. So there's an overall increase in the entropy of the universe. Energy flows into most ecosystems in the form of light and exits in the form of heat. And the evolution of biological order is indeed, like we said, consistent with the laws of thermodynamics. So we are hearing all about this energy floating around. Why? What does it do for us? Well, this energy that's able to do work, it's available to do work, is called free energy. You'll also hear it called maybe Gibbs free energy because it's named after this guy that kind of figured it all out, named J. Willard Gibbs. So what he says is that the free energy of a living system is energy that's available to do work when temperature and pressure are uniform. So we're not going to go too far into the free energy equation, how we actually calculate that free energy, but know that temperature and pressure are parts of it, and our change in energy, our change in free energy tells us if that reaction is spontaneous or not. So why do we care about whether or not a reaction is spontaneous or not? Well, it's really important to the study of metabolism, where a major goal is determining which reactions require energy and which reactions supply energy for cellular work. But how are we going to figure that out as biologists? First, we need to determine the energy changes, and we also need to determine the entropy changes to calculate our delta G, or our change in free energy. So spontaneous processes occur without energy input. They're favorable energetically because they don't require energy to be put into them for them to happen. And for a process to occur spontaneously, it must increase the entropy of the universe. Processes that decrease the entropy of the universe are non-spontaneous. They only occur if energy is supplied, if energy is provided to that reaction. And we can understand if a reaction is spontaneous or not by calculating our delta G. If our delta G is negative, it indicates that it is a spontaneous reaction. Well, how do we find whether our delta G, our change in free energy, is positive or negative? We take the free energy of the products minus the free energy of the reactants, and that gives us our change. So we can see in exergonic reactions, or reactions that are spontaneous and release energy, our reactants have more free energy than our products. This would give us a negative number, a negative delta G. And in endergonic reactions, our reactants have less energy available than our products do. So energy is required to make those reactions happen. They are non-spontaneous. So in review, we want to calculate our free available energy, or our Gibbs energy, to understand if a certain reaction is spontaneous and does not require input, or if a certain reaction is non-spontaneous and requires input of energy. We can calculate that by understanding our delta G, or our change in free energy. We get our change in free energy by finding the free energy of our products, and from that subtracting our free energy of our reactants. Free energy is the measure of a system's instability, or its tendency to change to a more stable state. During a spontaneous change, free energy decreases and the stability of a system increases. Now, once we get to maximum stability, we are at equilibrium. Once we are at equilibrium, we can no longer perform work. A certain process or reaction can only perform work when it's moving towards equilibrium and is spontaneous.